This self-study course is divided into 5 sections: basic circuit operation, electrical circuits, basic circuit designs, basic electronic circuit operation, and electrical measuring devices. To begin, we'll start with a quick overview of basic electricity. The basic elements of all electrical circuits are current, voltage, and resistance. Electrical current flows through a circuit in amperes, or amps. We use the letter A to symbolize amps. If a high amount of current is flowing through the circuit, the amperage, or amp rating of the circuit, is said to be high as well. And if there is only a small amount of current flow, the amperage is low. The amount of current flowing through the circuit is controlled by the load. A load is the portion of the circuit that uses up the current to cause heat, light, or motion. A high current draw, like this headlamp, will draw high amperage. And obviously, a smaller lamp will draw less current, or fewer amps. Voltage is the electrical force or pressure that will cause current to flow through the load in the circuit. Voltage is measured in volts. We use the letter V to represent volts. Resistance is the restriction of current flow through a circuit. Resistance value is measured in ohms. The Greek omega symbolizes ohms. A load in the circuit causes resistance, although resistors are also used in many circuits to reduce voltage before the load. Fixed resistors are used if full available voltage would damage the components, like these small indicator lamps and fuel gauge, for example. And stepped resistors are commonly used to regulate the speed of wiper motors and heater blowers. Certain types of resistors are also used as heating elements, such as rear window defoggers and cigarette lighters, since restricting current causes heat. Voltage, current, and resistance affect each other in a circuit. When voltage is constant, added resistance reduces current. And a drop in resistance will allow more current to flow. When resistance is constant, increasing the voltage will cause an increase in current. And lowering the voltage will reduce current. The flow of current follows a path from the source through the load and then to ground. Current can only flow through materials that permit it. These materials are called conductors. Conductors are usually copper or other metals and are used in wires and switches. Resistors are made of materials that are designed to restrict current flow in order to do work, such as producing light, heat, or motion. Now let's take a moment to review the elements of a basic electrical circuit. Voltage supplies the force that causes current to flow through a complete circuit. Voltage is measured in volts. Current flows along a path through conductors in the circuit. Current is measured in amperes, or simply amps. When current passes through a load or a resistor, there is a measurable restriction opposing the current flow, called resistance. Resistance, measured in ohms, can be deliberately added to the circuit, as in the use of heating elements or fan speed control switches. Voltage, current, and resistance affect each other in a circuit. If voltage is constant, increasing the resistance will reduce current. Decreasing resistance will increase current. And if resistance is constant, increased voltage will cause an increase in current, and reduced voltage will reduce current. Almost every circuit can be divided into 4 segments: the power or feed segment, the control segment, the load, and the ground segment. The power or feed segment runs from the voltage source to the input side of the switch. Next, in the control segment, the switch controls the power going to the third segment, the load. And the fourth segment grounds and completes the circuit. To simplify things, though, we'll divide the complete circuit into just two parts: the hot side of the circuit and the ground side. Some circuits have the switch on the ground side. Dome lights in passenger cars, for example, usually rely on a ground side switch located in the door opening to complete the circuit. Also, in many electronic control circuits, ground side switching through motion and temperature sensors has become very common. In these circuits, the components often have a distinct polarity. That is, they are sensitive to the direction that current passes through them, or which side is grounded. Many connectors, then, are designed to ensure that they are connected correctly, so the components will operate properly and to avoid damage to the circuit and the components themselves. Some locations where polarity is important are sensors and solenoids. Let's take a few minutes now to review what we've just talked about. So far, we've seen that electrical circuits can usually be divided into two segments: the power or hot side and the ground side. Remember also that some circuits and components are sensitive to how current passes through them. The polarity of the components, therefore, must match that of the circuit. You may already be familiar with some of them, such as sensors and solenoids. Continuing now, let's look at the three ways electrical circuits can be arranged. They are series, parallel, and a combination of series parallel. In a series circuit, the loads are arranged one after another, and the current through each load is the same. If you remember what we said about loads adding resistance in a circuit, then you know that after each load in a series circuit, the voltage is lower. This is how the dimmer control for your instrument panel lights work, as the dimmer switch is actually a variable resistor. And since the same current travels through the loads in a series circuit, should anything fail, the complete circuit will stop working. In a parallel circuit, voltage across each load is the same, and each load has its own path from the voltage source to ground. Resistance caused by one load does not affect any other load, as it does in a series circuit. And if one load fails in a parallel circuit, the others will continue to operate normally. Most vehicle lighting systems use parallel circuits. In a combination series parallel circuit, some loads have equal current passing through them, while others have equal voltage across them. Now, let's look at some circuits in operation. In this simple lamp circuit, current is continuous because there is no switch. Current will continue to flow until a component is removed from the circuit or until all of the available voltage is used up. Here we've added a switch to be able to stop current flow. If the switch is opened, then the circuit is open and no current can flow through it. An open circuit can also occur in other ways, such as a blown fuse, a cut wire, very high resistance due to damage or corrosion, or a damaged or broken component such as a burned out light bulb. In any case, current will not flow through an open circuit. Short circuits happen when an unexpected path to ground occurs. Examples include wires or components damaged in a collision, flood damage, or pinched and cut wires that can result from improper repairs. The location of a short in a circuit will affect the symptoms you find. For example, a short between the power source and the fuse will cause very high current flow and likely damage the circuit and the source. A short located here, between the fuse and the load, will blow the fuse and cause an open circuit. Merely replacing the fuse will only allow the circuit to operate briefly before the fuse blows again. Shorts can also occur on the ground side of a circuit, such as we've shown here. No components will be damaged by a short in this location, but current will continue to pass through this circuit even if the switch is turned off. Wire-to-wire shorts result from damage done to the circuit by an outside source. In a wire-to-wire short, current is allowed to take an unintended path or backfeed through different components. The fuse for the circuit remains intact, and signs that something is wrong are usually components not working right or working when they shouldn't. At times, feedback voltage or spikes are experienced in some electronic circuits. A diode designed to eliminate this is then installed in the circuit. This is how a diode is represented in a schematic. Diodes are conductors that allow current to flow through them in only one direction. They can, in low current circuits, be used to protect sensitive components from periodic voltage backfeeds or spikes that may occur. Diodes are also used in charging systems that use alternators to convert the alternating or AC current that alternators produce to DC or direct current. Now let's stop here and review the types of circuits, how they operate, and what kinds of conditions can cause current to stop or take an unintended alternate path. Electrical circuits are arranged in series, parallel, or in a combination of series and parallel. In a series circuit, the loads are arranged one after the other, and the current through each load is the same. If anything fails, all current flow in the circuit will stop. In a parallel circuit, each load has a separate path to the source and to ground, and voltage across each load is the same. Since each load is powered independently, the failure of one load will not adversely affect the others. Certain conditions called opens will cause current to stop flowing, and other conditions called shorts will cause current to take different paths than ones they are intended to follow. Sometimes, a circuit may have backfeeds or spikes of reverse voltage pass through it that could damage an electronic component. Diodes protect these components by only allowing current to pass through the circuit in one direction. So far, we've discussed a lot of the theory behind the basic operation of electrical circuits. Now let's look at some of the components. As we've seen earlier, electricity won't go anywhere without a conductor. Wiring harnesses are insulated conductors that simply carry current where it needs to go. Wiring harness connectors ensure firm, insulated connections at all times. For servicing the various types of connectors, refer to the appropriate section in the shop manual. Controlling devices used in electrical circuits include switches and solenoids. Switches are simply the on-off controls in electrical circuits. There are many types of mechanical switches that depend on the action of a component to complete a circuit. Brake lamp switches and the manual lever position sensor are examples of this type. Sensors allow variable control of voltage or resistance. Some variable resistors, such as the throttle position sensor, change their resistance value according to the movement of an attached component. Temperature sensors, or thermistors, are used to operate this temperature gauge, for example, since they vary their resistance value based on temperature. The speed sensor is used in place of a speedometer cable and converts magnetic pulses into a voltage that can be used by the electronic speedometer and the EEC4 control unit. Solenoids are electromechanical devices that convert electrical energy into mechanical energy. As electrical current travels through the outer portion or electromagnet of the solenoid, the resulting magnetic field forces the center core to pull in or push out. You've probably come across solenoids already while servicing starter motors, power door locks, and trunk lock mechanisms. In electronic automatic transmissions, solenoids are used for shift controls and converter clutch operation. Now let's review this section on the wire harnesses and connectors, switches, sensors, and solenoids. Wiring harnesses connect the electrical components throughout a vehicle's electrical systems. Some components called switches simply turn current flow on and off. Resistors that can control their value based on temperature, motion, or the position of a lever are called sensors, such as a temperature gauge sensor, the speed sensor, and throttle position sensor. Solenoids are electromechanical devices that transfer electrical current flow to mechanical movement, such as starter motor solenoids, electric trunk lid releases, automatic transmission gear shift solenoids, and torque converter clutch solenoids. Electronic control systems depend on three types of devices to operate, namely input, processing, and output. Input devices are usually sensors and switches that monitor specific conditions and components. Devices such as the airflow sensor and the turbine speed sensor are continually monitored by the control unit, or processor. The processor is a computer. Based on all the information it receives from the input devices, the processor controls solenoids and other actuators, or the output devices. The EEC4 control unit is the processor for many drivability and transmission shift routines. Output devices are usually types of solenoids that change electrical current into mechanical action. They are replacing bulkier manual or mechanical devices in many control systems, making them fully electronic. Solenoids in automatic transmissions can be the regular on-off type that have a single in and out core movement, or a variable force design. Variable force solenoids control the amount of core movement depending on the varying ground provided by the processor. These are used to control transmission shift feel, for example, by varying the amount of applied pressure. Operation of the torque converter clutch in some transmissions is also controlled by a variable or modulated solenoid that allows a controlled amount of slip to occur during clutch engagement. Another feature of electronic control systems is their ability to monitor themselves for signs of trouble and record any input failures that occur during normal vehicle operation. These can be retrieved later during your diagnostic routines. Now let's take a moment to review electronic control devices. Electronic control systems are a combination of three types of devices. Input devices, located at various locations, are constantly monitored by the processor, an electronic control unit that then controls the ground for the output devices that are usually variable force or on-off type solenoids. To help you in diagnostic routines, electronic control systems can also record occurrences of input failures for later retrieval during self-tests. In order to test electrical circuits and components, you'll need an analog or digital volt-ohm meter, or multimeter. The typical analog multimeter, like this one, has numerous scales to cover voltage, amperage, and resistance, or ohms readings, depending on which you select. The digital multimeter, sometimes called the DVOM for digital volt-ohm meter, is capable of measuring the same values, but it displays only the value measured and in the range you have selected. While analog meters are relatively accurate, they can be confusing, and some versions can allow a damaging amount of current to pass through delicate electronic components while you're testing them. Digital meters, however, are more accurate and easier to read. Most of the electronic testing you will be doing requires the use of a digital multimeter for better accuracy. But more importantly, digital multimeters won't draw or deliver excessive current that will damage sensitive components. All your electronic testing should be done using a digital multimeter. And whenever you use either type of ohm meter, you must always zero the meter by connecting the test leads together and setting the scale to 0. When using a digital ohm meter, zeroing is sometimes automatic. When it isn't, simply subtract the resistance you get when touching the leads together from the readings you get during your tests. The DVOM is used to check components and circuits, including internal tests of input and output devices using a breakout box and jumper wires with compatible ends. The transmission tester is used to separate electronic transmissions from the vehicle processor for diagnostic purposes. When connected in place of the vehicle harness, the tester functions as a computer and provides the same signals that are sent by the vehicle processor. In this section, we've briefly discussed the types of testers used to diagnose problems with electrical circuits and components. A digital multimeter, or DVOM, an electronic control system breakout box, and some jumper wires, and the transmission tester are needed to make most of the tests you'll perform when diagnosing transmission, electrical, and electronic systems and components. And it's very important to remember to use a digital tester, or DVOM, when testing electronic circuits and components to safeguard against damage from excessive current that can occur when using analog-type meters. You have now viewed all 5 sections of this Electrical Basics training course. You should now have a basic understanding of how electrical circuits work.